Are functions just naturally difficult for people to understand?
I don't think so. In fact, while creating this entire series, I was pretty surprised at how competent people were with their knowledge of functions.
What do you mean?
Okay, so a simple example of the mathematical notation, which is very common, f of x, it's not being used properly, but the language is there. When I say it's not being used properly, I just mean when you look at it out in the wild, right? Mathematicians would normally say f of something, f of 5, f of 10, whatever it is. That just indicates that they have a function f and that it's evaluated at 5 or 10, whatever I just said. I found that instead of saying f of something, people are essentially saying, here is 5. Instead of even saying apply f to that, they just say f that. So the Urban Dictionary has it. There's a TV series all about it, right? There are card games that have been created that kind of center on this idea. There's even a meditation video. Pinterest is jumping in on this. And in that case, they have a whole page dedicated to applying functions to noise variables, some type of signal analysis. So to answer your question, no, I really don't think that people are struggling with functions.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, I will reintroduce as a review the basics of functions. We were not going to get too far into the gritty details here. We're just defining and kind of getting used to, or reused to, I guess, if that's a word, the basics of functions. So let's go ahead and get started. A function is just a relation. That means just an equation in a way. It's a way to tie two variables together. So it's a relation that takes a single input or an input, we call the independent variable, and transforms that into a single output. And we call that single output a dependent variable. That is the critical point here, is that it transforms that input to a single output. That's very, very important. That's the defining characteristic of a function. Now, before we go too far ahead of ourselves here, I'm just going to write the layperson's version of this definition. So a function is a machine that transforms an input to a single output. This is essentially what I just set up here in the rigorous definition. But this one allows me to kind of give you a better idea via a picture. So I'm going to draw what we call the machine diagram here so that you can see what I'm talking about. Trust me, that's supposed to be a machine. Okay, and we have some conveyor belt here, and along this conveyor belt is a variable, and it's just heading into the machine. We shall name the machine. Let's call this machine F, because that is the traditional name for these machines. They're called the functions F. We plug into that machine a letter or a variable X. We don't know what's going on in here. It's like a little black box, and out pops a completely different value. It doesn't have to be completely different, but often it is, and we shall call that Y. However, notationally, we are going to eventually just call that F of X, which means that that is the output when I plugged X into the function machine. This is called a machine diagram. It gives a good kind of picture of what a function does. So starting with the idea of domain, the domain of a function that I'm calling here F, the domain of a function F is the set of all values for which the function is defined. Now, since it's a review, you do have the ability, or you have seen functions in the past, so it's not so illegal for me to go ahead and jump ahead and just say, well, if our function, f of x, is equal to, let's say, 3 times the square root of x minus 1, or some silliness like that, That's our function, our relationship between inputs and outputs. There are restrictions on that. This function is not well defined at 0, because if you plug 0 in, you have a complex valued number that gets popped out, right? It's the square root of -1, which is an imaginary number. So to keep everything real, in this case, the domain, which I'll just use D here for the domain, is all values of x such that x minus 1 is greater than or equal to 0. And of course, that's a little simple solve there, right? X must be greater than or equal to 1. And so those values of x would be the domain of this given function. Now, a lot of people think, and by the way, I'm just going to write it this way as well in interval notation. A lot of people think that just because they've been handed an equation or a function in equation form, that the domain just requires, to find the domain, they just have to do some algebra. But there are times when you're given a function in equation form where they also give you a restriction, right? So maybe g of x, a different function, is equal to 3 times the square root of x minus 1. But they give us a restriction that x must be between 1 and 5. So in this case, because I already know that original function can take any x value that's greater than or equal to 1, and they further restricted that to say, I want my values between 1 and 5, inclusive of 1, but exclusive of 5, then the domain of this function g is going to be 1, including 1, all the way up to 5, but not including 5. So there are ways that we can artificially restrict the domain of a function. So the range of f is the set of all possible outputs given the domain. So again, you have to think of the domain is sort of a restriction just based upon either what we're handed. Somebody says, oh, well, I won't let you plug in any x values between or beyond 1 and 5. Or it just might be given by the function. Like you look at a function and you could tell the domain is everything greater than or equal to 1. The range, on the other hand, are all the possible outputs that depend upon those inputs. So, and we'll see examples. But for now, we should move forward. There are actually 4 representations of functions, and so just to quickly go through them, there are tables, equations, graphs, and those dreaded word problems, or what I like to call applications. So just to showcase tables, this table represents a function because remember, the defining characteristic is that each input leads to a single output. If you take a look at the inputs here, the input of 1 leads only to the number 2. The input of 3 only leads to the number 2. The input of 5 only leads to the number 1. The input of 7 only leads to the number 8. The domain of this function is 1, 3, 5, and 7. The range of this function is 2, 1, and 8. And if you look there, I've listed it out in roster notation. Notice that for the range, I didn't bother writing 2 twice. There's no need for that. 2 is just an element of the range. There's no need to list it twice. That is considered bad form if you do that. I was just about to do another example, but before I move on, I just want to say, so therefore this is a function. Maybe I should write it this way. I'll just say FNC. So I use FNC to tell the world this is definitely a function. Now, creating a different table here, x versus y, I could write 1, 1, 1, 1 leads to 0, 1, 2, and 3. If you take a look at this, the input of 1 leads to 0, but it also leads to 1, it also leads to 2, it also leads to 3. Because that single input of 1 leads to multiple outputs, this is not a function, FNC. So this is kind of the easiest way to tell whether a table represents a function or not. It represents a function if each input leads to a single output. It's not a function if there are 2 of the same inputs leading to different outputs. Examples of functions as equations Well, here's one. There's not much I can really say about this other than to talk about the domain, which we already have. We didn't really talk about the range, but that's something that I would recommend doing using graphs. Another function, and just to let you know, you don't have to always use the letter F, is what we call piecewise-defined function. You should have seen these. Maybe that's x squared plus 1 as long as x is greater than or equal to 0, and maybe a negative x minus 1/2 as long as x is strictly less than 0. So that would be a function, because depending upon what you plug in, if I plug in 2, getting a little bit ahead of myself here because I'm assuming you have seen function notation, which I'm about to define. But anyhow, if you plug 2 into this, well, 2 happens to be greater than 0. And therefore, what I can do is I can go ahead and plug 2 into that top version of this, or the top formula, right? So 2 squared plus 1, that's 5. Whereas if I plugged in, let's say, negative 5, well, negative 5 happens to belong to the second set. That's why it's called piecewise. That second piece is what negative 5 belongs to, because negative 5 is less than 0. Therefore, I would plug in the opposite of a negative 5, and then minus 1/2. Now that's just evaluating a function, but I just want to give you those two examples. So what other forms did we mention earlier? I'll scroll up just to showcase it. Let's see, tables, equations, graphs. All right, graphs are kind of the easiest. And that's because a graph, for it to represent a function, you just have to remember one defining characteristic of a function, that each input must lead to a single output. So in this case right here, what I've drawn is going to be a function because each of these inputs, 1, 2, 3, 4, lead to their own single outputs, right? So this is definitely a function versus something like this, where an input exists. This might be a negative 2, let's just pretend, and it leads to 2 different outputs. That is not a function. So I'll write that in, not a function. So I write the vertical line test a little bit differently than some other people. I just think the language is a little bit easier to understand this way. So if there exists, so if somebody draws a graph for you and you can create a vertical line which strikes the graph more than once, then the graph does not represent a function. So otherwise, it does represent a function. So in all other cases, it will represent a function. So again, let me just go ahead and use this theorem very quickly at the 2 graphs above. Remember, if I can draw a vertical line that strikes the graph more than once, then it is not a function. So any vertical line that I put on this first graph will never strike more than once. So therefore, that first graph is a function. But I can easily create, I understand this vertical line doesn't strike the graph more than once, right? This line doesn't strike the graph more than once. But if there happens to exist a single line in the universe, a single vertical line that strikes the graph, well, it's supposed to be vertical, more than once, then you know that graph is not representative of a function. The final representation, which is word problems here, that is going to be just for a different video altogether, just because it's a little bit bulky to get into in a short period of time. So quick definition for function notation that you should already know from your prerequisite courses is that if f is the function name, it doesn't have to be, it could be g, h, or anything else actually, and if x is the independent variable, then we define f of x to be the value of the function at x. Again, that is read as f of x. That's not a multiplication, that is an evaluation, f evaluated at x. We come to the final part of this video. I'm not going to do examples here or how to work with functions here, just because this is a big enough video by itself with definitions. But I do want to talk about where you see them. And that would be starting with algebra, basically algebra 2 and beyond. And I'm not saying that you rarely see them or you sometimes see them. You actually see them all over the place. They become the defining characteristic of transfer level mathematics. So you really do have to be pretty solid with your understanding of what a function is and be able to deal with functions easily to be successful in transfer level mathematics. Okay, well, thank you for watching this video on reintroduction to functions. As always, this content should be prerequisite to the course in which you're currently enrolled. If you found this material unfamiliar or if it was confusing to you, then I recommend you click on the provided relevant prereq links listed below for further help. However, if you find you are continually doing this, you might want to consider speaking with your instructor about other course options. On that note, I sincerely hope these videos help you achieve success in your transfer level math and science courses. Cue the music.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.